I received the bio of Xuan Wang, and it was way too long to tell everything. So I shortened it a little bit. She is a fifth-year PhD student at the Computer Science Department at the University of Illinois in Urbana-Champaign. And she is working under the supervision of Zhao Han. And when I saw that, I was thinking, if somebody wakes me up in the middle of the night and says, who's the most famous person in data mining, that's the name that I would produce. And her research is in interesting areas to me personally. So natural language processing and data mining with applications in biomedical informatics. And her two main directions are information extraction with minimum human supervision and literature-based scientific knowledge discovery. And Xuan has 20 research papers in major conferences and journals, and is also a recipient of a Best Paper Award at NAACL and a Ye Fellowship Award in 2020. So please go ahead. We're looking forward to it.
Thank you very much, Dr. Geller, for the introduction. Hi, everyone. This is Xuan Wang from University of Illinois at Urbana-Champaign. Today, I'm very honored to be here to introduce my work on this automated scientific knowledge extraction from massive text data. So nowadays, we're buried in this massive text data in our daily life. For example, we have those news reports, social media tweets, business and financial documents, scientific papers, and also those medical records. And plus, the amount of data is growing exponentially every year. So what can we get from this massive amount of text data? So we can take a look at an example. This is a sentence we got from a scientific literature. It's in the chemistry domain, and we can take a look at this sentence for a few seconds. And we can see that this is actually a very complex sentence. And if for people like me, we do not have much domain knowledge, we do not know actually what's inside this text data. However, if we ask human experts to look at the sentence, they will be able to quickly extract a lot of meaningful knowledge. For example, those aldehyde and some others, those are some organic compounds, and there exists this chemical reaction in this sentence. And plus, they know that this reaction will has an excellent yield. So we can see that human experts can actually find a lot of useful information from the published scientific papers. However, if we rely on human to do this knowledge extraction, then this process can be very slow and time consuming. So the question is, can we automate and speed up this process with computers? We know that computers are very reliable and good at data processing, but when it looks at this scientific literature, to the computers, it's just a list of character strings, although this speed is very fast. And my work is to bridge this gap between the information computer can get from text and the knowledge that can be understood by human. Basically, I'm developing those text mining algorithms that can be fast and efficient so that we can turn those text data directly into knowledge and insights for human to use. So how can we automatically turn those unstructured text data into knowledge and insights? So the key here is we want to first turn the unstructured text into some structured formats. And based on those structured formats, it's either to be processed by the computers for the knowledge discovery. So the first step is that I want to automatically extract the information, such as entities and relationships from the literature with methods in named entity recognition and relation extraction. Then based on the extracted information, I want to build some intermediate structures, such as those multi-dimensional text cubes or those knowledge graphs or knowledge networks with techniques such as text classification and knowledge graph construction. Then based on those structured data, we will be able to do some further knowledge discovery to benefit some real world applications. So here's an overview of my work. I basically focus on two directions. First is this information extraction with minimum human supervision. And I have been working on tasks such as named entity recognition, open relation extraction, and text classification. The second direction is literature-based scientific discovery. And I have been working on some real-world applications, such as automated textual evidence mining, literature knowledge graph construction, and also drug discovery with text analysis and chemical reaction knowledge-based completion. So in this talk, I will cover part of my existing work. Mainly, I will first talk about two pieces of my work in this named entity recognition with minimum human supervision. And the second, I will briefly talk about a real-world application of how we use text mining to aid this drug discovery process. And last, I will give a brief summary of my work and also some future directions I want to further explore. So we can first look at this task, named entity recognition with minimum human supervision. So this task of named entity recognition, or we call NER in short, aims to identify those entities in text and also classify them into some predefined categories. For example, we can see in this sentence, Jim bought 3 shares of Acme Corp. We want to automatically detect that Jim should be a person entity and this Acme Corp should be an organization entity. And this entity recognition is a fundamental task in the whole information extraction pipeline, and it can benefit many downstream tasks such as relation extraction and the knowledge graph construction. So the prior state of art in NLP for this NER task are mainly some supervised machine learning methods. So basically, they will first have some human labeled training data. Like here, I show an example of the human annotation interface. Basically, they need a human to read all of those sentences, then to mark out where is an entity and what type this entity belongs to. Then after they collected a large amount of training data, they can train a sequence labeling model so that when we have a new sentence, we'll be able to recognize like which one should be a person entity and which one should be an organization entity. And there has been a lot of work done under this supervised setting, and it has been extensively studied. However, the major limitation of the supervised NER methods is that they rely heavily on this corpus-specific human labeling, which means that they cannot be easily generalized to new types or new domains. For example, when we have this COVID disease, there are a lot of COVID-related specific types, such as coronavirus or those immune responses that we cannot directly collect a lot of human annotation. And we cannot easily transfer the previously trained models on other tasks to these new tasks. So my solution here is that instead of asking human to give us labeled data, I want to do it in a distantly supervised setting, which means we want to leverage some existing domain-specific knowledge bases to help us automatically generate this large amounts of training data. Then we can design models to do the prediction based on this automatically created training data. Here's an example. Say those are the sentences we get from the COVID-related corpus. And in addition, we can get some domain-specific knowledge base. For example, this UMLS for the biomedical domain. And in the knowledge base, we'll be able to get many fine-grained entity type hierarchies. For example, we will get coarse-grained types like genes, chemicals, or disease. And for each coarse-grained type, we can even go down to very fine-grained ones, like a virus or coronavirus. And also for each fine-grained type in the type hierarchy, it is associated with an entity dictionary in a knowledge base. For example, coronavirus, we know SARS-CoV, MERS-CoV, these are all known coronavirus. And we can use those entity dictionaries to automatically label some of the raw text data so that we can automatically generate a large amount of training data to train our sequence labeling model for this NER task. However, there are some challenges for this distantly supervised NER. The first challenge is missing annotation because the knowledge bases may not be up to date and may not be complete. So there could be entities that are completely missed during this KB matching process. For example, in this sentence, this SARS-CoV-2 could be a very new concept, and it's likely that it does not exist in the existing knowledge base. So during the training data generation, we will miss this entity and we will not label it as a coronavirus. The second challenge is partial annotation, which means some entities can be partially matched in the knowledge base. For example, in the biomedical domain, we see this alanine aminotransferase. This whole thing should be a protein. However, it's possible that this long phrase does not exist in the dictionary, while part of it, this alanine, can be found in the dictionary of chemicals. So by KB matching, we partially match this one as chemical, but we lose this whole one as a protein. The third challenge is this multi-type annotation, which means that entities can be matched to multiple types in a knowledge base. For example, in this sentence, this palladium here can be matched to a catalyst or transition metals in a chemistry knowledge base. However, if we look at the sentence or the paragraph, we know that under a certain context, only one of those candidate types is the most appropriate one, or the most correct one for palladium here in the sentence. So that by KB matching, we face this problem of multi-type ambiguity that we need to resolve before we can train a reliable model. Then how can we deal with these three kinds of challenges in distant supervised setting? There are many methods that has been proposed. Most of the existing distantly supervised NER methods are usually model-driven, which means they want to leverage a deep learning model by trying to make the design more suitable for this imperfect annotation. However, we observe that by leveraging one deep learning model, it's usually very hard to solve all those three challenges. And plus, there's a significant gap in the performance compared with the fully supervised NER models. So my solutions are actually more data-driven, and I have been developing the several data-driven mechanisms that can solve each challenge in the distant supervised setting. And those data-driven methods can be easily integrated with each other, and they are usually of a very high effective. And here I will introduce two works that address two of those challenges. First is this panel called Pattern Enhanced Nested Named Entity Recognition in biomedical literature. So this work mainly aims to address this partial annotation problem. Just to remind you that this partial annotation usually is resulted from some nested naming structures of the entities. For example, this whole thing should be a protein, while part of it is actually a chemical that can be matched in a knowledge base. These nested entities are actually very important and especially common in the biomedical domain. We have observed that more than 17% of the entities in this GENIA biomedical benchmark corpus are actually embedded within one another. So our question is, how can we automatically correct those partially labeled entities to recognize the outermost entities with these nested naming structures? So the key idea in my panel work is to use pattern mining. And we want to do this nested entity recognition with very weak supervision. basically we observed that those nested structures can be recognized as a pattern level phenomenon. For example, this alanine aminotransferase, if the knowledge base can only match alanine as a chemical, and we can replace this original entity with this type here, then this whole thing becomes a pattern chemical aminotransferase. As long as this chemical aminotransferase appear very frequently in the corpus, then we are confidently to say that this pattern is very likely to be an alter entity that is partially matched in the previous step. So we first get those patterns, then we try to find which type this pattern refers to. For example, here it refers to protein. Then after we got those information, we can use those typed patterns to go back to the corpus to correct those boundary detection problems. Yeah, so in summary, we first conduct an unsupervised meta-pattern extraction. Then we conduct a few short new entity recognition by classifying the patterns into different types. So we can look at the overall framework of panel here. First, we will have some input corpus with all those raw sentences. Then we'll do a first round of flat entity recognition, either by some existing NER methods or by our knowledge-based matching. Then during the first round, we can match some entities in this corpus. After that, we will replace each entity with its type, then conduct a meta-pattern extraction to find all those patterns that can serve as our potential alter entities. Then we want to know that which type each pattern refers to, and we will give maybe 2 to 3 seeds for each type to do an automatic seed set expansion so that we can gradually put each pattern into the correct type set. And after that, we'll use the expanded pattern set to go back to the entity tagged corpus to correct some boundaries of the previously recognized entities. And we can take a closer look at each step. The first step is meta-pattern extraction. And by meta-pattern, we refer to those textual patterns containing entity type tokens. Like we mentioned here, this alanine aminotransferase can be replaced with a pattern chemical aminotransferase if we replace the entity with their type. And then we can conduct this meta-pattern extraction. Basically, after we replace the entity with their type, we will conduct a frequent sequential pattern mining to find all those patterns as our candidates. Like here in the original sentence, we have this species human telomerase. And if we replace this human with the type species, and after some pattern mining, we are likely to find this species telomerase as one meta pattern that are likely indicates some new entities, for example, proteins. After we got all those candidate patterns, we want to know which concrete entity type those patterns refer to. So we conduct this weekly supervised pattern expansion. Basically, we want to find new patterns for each entity type with user-specified seeds. And our solution is to rely on skipgrams and the rank ensemble to do this pattern set expansion. So this is the overall framework. First, we will get some user-given seeds for each type. Say for the gene type, user may give us 2 to 3 seed patterns like camino peroxidase. Then we will leverage some context information from the corpus, basically the skipgram information, to find more patterns belonging to this set. For example, species telomerase and chemical kinase. Both of them could also refer to a gene entity. And how exactly we leverage the context information for the pattern set expansion is that we leverage the algorithm called the set expand that is originally designed for the entity set expansion. So given several entities like Illinois, Virginia, and many others, we can automatically find the surrounding context, say city, USA, or US state of that can indicate that those are some state entities. Then we can randomly select several sets from this whole context set, and you use each set to rank several other potential candidates. Then we finally undouble all the ranked lists together, and we can get a more confident ranked list. And we can see that in the final ranked list, all the top entities are high quality states in the US. And we use this similar strategy for pattern expansion. Basically, we also get a skip grams for all the patterns in the corpus, and use all those skip grams. We rank more patterns, and we gradually expand the pattern set. And as we mentioned, this expansion can go in several rounds, and we can iteratively add in more quality patterns. This pattern set expansion is very effective in capturing new patterns for each type set. However, it also has one limitation, because the original set expansion method is designed for entity sets, and they actually expand each set independently. And by using that algorithm, one pattern may be wrongly expanded to multiple sets in different rounds. For example, here we can see gene expression. It is first expanded in its biological process set, while after several rounds, it will also be expanded in a gene set, which is actually not the correct expansion here. So our solution here that instead of expanding each set independently, we do a multi-set co-expansion with mutual exclusiveness. Basically, if we see one expansion has already appeared in other sets during the previous rounds, we will know that it's likely to be a wrong expansion, and we will remove it in the current step. So after this several steps, we will be able to get those high quality patterns, and we can use those patterns to go back to the corpus to correct the entity recognition results. We compare our performance on a very large data set of the PubMed abstracts that are initially annotated by a pubtator, state-of-the-art supervised NER method. Then we measure the quality of our expanded entity list with several different methods. Like we have compared with some biomedical word embedding methods. We also compared with the initial set expansion method. And we can see that in general, panel can achieve much better performance compared with the previous embedding-based method or the original set expansion method. Moreover, because this method is totally weakly supervised, so we can easily detect new entity types with very few seeds. For example, we can detect a biological process, this new type, with only 2 seed patterns. The original pattern we gave is gene upregulation and gene downregulation. And during the expansion, we will be able to recognize more, such as gene expression and gene phosphorylation. And we further examine the results, and we see that one possible improvement is that if the gene types can be more fine-grained, we will be able to recognize the types better. For example, we have one pattern called a chemical exposure, and it can mean different things if the chemical is different. For example, if this chemical refers to some drugs like resveratrol here, then chemical exposure in the text usually refers to some treatment. However, if this chemical refers to some toxics, say this mercury here, then this chemical exposure is more likely to refer to some symptoms in the text. So this motivates us to further study how we can recognize not only the coarse-grained entities like gene chemical disease, but also much more fine-grained entity types. Then I will introduce the second work called ChemNER, which we try to automatically recognize fine-grained chemistry entities with ontology-guided distant supervision. And when we go to this fine-grained entity recognition, the multi-type annotation becomes a more severe issue. So here in this work, this ontology-guided distant supervision, we actually want to address this challenge of multi-type annotation under the distant supervision setting. We can see this example here. This palladium can be matched to 2 types, catalysis and transition metals in the original knowledge base. And we want to automatically disambiguate these two to find the most correct one. In fact, this multi-type issue is very severe for the chemical entities. And we observe that more than 60% of the chemical entities in our corpus has multiple types if we go to the fine-grained anti-recognition. And on average, each chemical entity can be matched to 4 types by our knowledge base. So we designed this method called ChemNER, which tries to assign the most accurate fine-grained type to each mention under certain context in text with ontology-guided multi-type disambiguation. So we can look at the overall framework of ChemNER here. First, we also got a raw corpus without any annotation. Then we leverage some phrase chunking tools to automatically detect some entity spans as our candidate entities. Then we leverage some flexible KB matching method to assign several potential types to each candidate mentioned in our sentence. And after that, we want to disambiguate those multi-types for those entities in the sentence by leveraging both its context and also the structure of the type ontology we use. And finally, taking the data from the previous 3 steps, we use it as a training data to train a sequence labeling model to do our final NER prediction. We can first look at the first 2 steps. Entity span detection and flexible KB matching. As we mentioned, after we got these raw sentences, we want to first find some candidate entities we want to assign type to. And here we use some state-of-the-art chemical phrase chunking tool, chem data extractor and a gene tagger that can automatically give us high-quality chemical phrases. After that, we want to use the knowledge base to assign several potential types to each entity. We observe that for those chemical entities, they are special in that they usually have those long and complex naming structures, so that if we do a simple string matching with the knowledge base, we will miss a lot of entities. So here I propose this TF-IDF-based majority voting. Basically, I split a long entity into several tokens, like this methyl 14KSDTH here. It can be break into methyl, THD, and many other tokens. Then for each token, we let them vote for several types in the knowledge base that are most likely contain this token. And after this kind of voting, we can combine the voting from all those tokens in a single long entity, and we can pick all those top ranked types as our candidate types to assign to this entity here. By this flexible KB matching, we'll be able to match many chemical entities that does not exist in the knowledge base in the original formats. Then after we assign several potential types to each entity, we want to further disambiguate the types to find the most appropriate one under the certain context. Here we leverage both the text information and also the chemistry ontology information. This ontology we automatically constructed from the Wikipedia. Basically, we collected all those Wikipedia categories rooted under this chemistry category as our entity types. Then for each category, we'll be able to find their associated page titles to form our entity dictionary. And by this kind of automatic ontology construction, we will be able to construct an ontology of 62 fine-grained types in the chemistry domain. We further incorporated some chemistry domain knowledge base, such as PubChem, to further enrich the dictionaries of each type by including some more entity synonyms into the dictionaries. Then based on this type ontology structure, we will be able to do this ontology-guided multi-type disambiguation. So the key idea here is that we assume the entities in the same sentence, paragraph, or document usually follow a focused topic. For example, we can see this long sentence here. in this sentence, this palladium will be mapped to two potential types, catalyst and transition metal. And if we look at the chemistry ontology structure here, we can see that on the top level, those nodes usually refers to some very focused topics or subdomains in chemistry, such as chemical reactions or chemical elements. And we can see that for those candidate types, this catalyst actually falls under the branch of chemical reactions, while these transition metals fall under the branch of chemical elements. How can we know which one is correct? We further look at the context of other entities in the same sentence. For example, this cross-coupling, it has type coupling reactions. And for functional groups, it has the type functional groups. We can see that in the surrounding context, these two entity types are generally also fall under the branch of chemical reactions. So by looking at the surrounding context, we are more confident to say that this whole sentence is more likely to be talking about some chemical reactions rather than some chemical elements. So that we know that for palladium here in this sentence, it is more likely to have a type catalyst instead of transition metals. More specifically, we define this disambiguation score here to help us decide which candidate type is more correct. And in this equation here, we can see that this TEIG here refers to all those candidate types for this entity dimension EI. And this TEK here refers to the types of all the other entities in the same context or in the same sentence with EI here. So this LCA here basically measures the lowest common ancestor of those two type nodes on the type ontology. And this depth here measures the depth of the type node on the type ontology. So in general, we can understand that this numerator here measures how close are the candidate type with all other context types along the type ontology. And this denominator here is a normalizer, which measures how fine-grained it is for this candidate type on this type ontology. So in general, we will see that a larger disambiguation score will means that this candidate type is more likely to be correct. Last, after these three steps, we will be able to get a very comprehensive and very clean training data to train our subsequent sequence labeling model. So as we mentioned, even we do very careful designs of flexible KB matching and multi-type disambiguation, it still cannot cover all the possible new entities in the corpus. So we further train a sequence labeling model to improve the recall. And we use some standard NER models like Roberta and Camberton that are based on some pre-trained language models. And here we hope that it can further uncover some new entities such as BBA here, those kind of aberrations that cannot be covered by the previous two steps. Last, we compare our performance with our baseline methods. Our data set involves a training set which contains 75,000 unlabeled sentences and also this 62 fine-grained chemistry types we collected from Wikipedia. And for the test set, we will have 3,000 expert annotated sentences to compare the performance between different baseline models. So here's the performance comparison. We have compared CAM-NER with some simple KB matching method and also some state-of-art supervised NER method, such as this BioSTM CRF, Roberta and Camberta here. We also compared with some state-of-art distantly supervised NER methods, like auto-NER and bond here. We can see that compared with the best performing supervised baseline Roberta, this CAM-NER here can achieve a substantially better performance with almost a 25% absolute F1 score improvement. So that is the work I have been done for this named Antirecognition under the distantly supervised setting. We can see that with the distantly supervised NER methods, we can automatically recognize a large amount of very fine-grained entity types for different domains without human effort for training data annotation. Then I will talk about an application here where we use our fine-grained information we automatically dig out from literature to support some clinical applications such as drug discovery. So this is the work called Sun Contrast, which is called scientific topic contrasting from life science literature. We first got some questions from the clinical researchers. Those are our collaborators in the UC Davis Medical School. Basically, those are the doctors working on the heart diseases. They have 6 main categories of heart disease, and they want to find what could be the potential drug targets or the proteins that are specifically related to each heart disease. So here is an example. As we can see, those are the 6 heart disease types. And from the literature, by reading the literature, we'll be able to find a lot of, proteins or genes. And the task here that we want to find which genes is specific for which disease, which means this gene should be relatively very relevant to this disease, but much less relevant to all the other categories of diseases. And here we involve a lot of our previous work, including fine-grained information extraction, comparative text analysis, and the textual evidence discovery to find those targeted proteins, and also to provide some text sentences as supporting evidence. And more specifically, how we do this comparative text analysis. So given those human input disease categories and all the proteins we automatically find from the literature, we want to measure the score of each protein for each disease as a potential target. And we measure 3 scores here. The first is called integrity, which measures how the protein name is to serve as a valid protein name from our text mining algorithms. Second is this distinctivity. And here it measures how the protein is exclusively related to a particular disease category compared to the other remaining 5 categories. And the last is popularity, which measures basically how popular or how relevant this protein is to this particular heart disease category. And our final score, called the KSOLAB score, will be the multiplication of the 3 scores. And in general, a protein with a larger score will be ranked higher for that particular disease. And we have validated our results in the 6 groups of heart diseases by comparing with several baseline methods, including some traditional information retrieval methods like TF-IDF, BM25, and a query language model, and also some recent pre-trained language models such as BioBERT in the biomedical domain. And we asked the clinical researchers to give a score for our top-ranked proteins by all those methods, and then we will be able to calculate the NDCG score for each ranked list. And we can see that this Sun contrast here actually achieves the best performance compared with all the baseline methods. Moreover, the doctors have been using our method and the results for some real clinical applications. For example, our collaborator in UC Davis Medical School are currently focused on these 2 diseases, HFpEF and HFrEF. And here we can see that we will provide those top-ranked protein lists as some potential drug targets for them to further explore. And this collaboration has been very fruitful. It actually leads to some future development of precision medicine approach for this HFpEF disease, which currently do not have any effective treatment for now. And it also leads to a recent NIH grant to support this study of this HFpEF and HFrEF diseases. We're also further extending this collaboration with UC Davis and Harvard Medical School, where we want to build this multi-omics data mining platform, which means that in addition to mining the scientific literature, we also want to look at other clues, say from electronic health records and also maybe some genomics data to combine different information resources to better facilitate those drug discovery processes. That is one real-world application we have been doing with our text mining algorithms. Last, I will give a brief summary of my work and also discuss some future directions I want to further explore. So as a summary, my work mainly focused on this scientific knowledge extraction from massive text data. And as we have discussed, taken some raw text data as input, I first automatically extract information such as entities and relations. Then we construct some intermediate structure like a multi-dimensional cube or knowledge graphs and use those structures to facilitate our knowledge discovery process. So for some future work and collaborations, I believe text mining can have a lot of collaborations with other AI and data science fields and also other engineering and science fields outside the data science domain. So first, for the text mining itself, I want to further explore new text sources and also new information types to be mined. Like I have mentioned, in addition to those scientific literature, we can also explore, say, those health, electronic health records and also text from other domains. Anywhere if people have these needs of automatic knowledge extraction from massive text data. And also, in addition to those entities and relations, we can further extract other information types. For example, those relation conditions and also experimental procedures as a sequence of events automatically from literature. And those various more complex information resources can also help us to do some more complex downstream tasks. Then in terms of collaborations with other AI or data mining fields, I think there are potential collaborations with, say, people doing graph mining, computer vision, also machine learning. For example, the text mining can be integrated with graph mining by building some text-enriched information networks and developing new mining methods. Like I mentioned in my previous work, I mainly focused on text and extract some text knowledge graph. While there can be some already existing well-established, say, heterogeneous information networks for, say, for biological domain in the existing knowledge base, like those gene regulatory networks. And how can we incorporate the text data with the existing network data to form a more comprehensive network structure to facilitate the mining process? This is one future direction I want to explore. Another direction is for this combining text mining with some image analysis or computer vision. For example, we can construct a multimodal knowledge graph based on linking the information in text and the graph. For example, this is an example in the chemistry domain where they have a lot of these chemical elements in the graphs or tables, and there are also many text descriptions of the entities in text. So if we can further extract information from graph and link or align those information with text here, we'll be able to construct this multimodal knowledge graph to better facilitate our knowledge discovery. And also, as we mentioned, this text mining can also be facilitate other science or engineering fields, such as bioinformatics, bioengineering, and maybe other science and engineering. This is an example of using text mining for some bioengineering applications. And this is mainly a collaboration between our group and the chemistry department. for chemical biomedical molecule synthesis. And for me, my work is on the very first step to automatically construct this chemistry knowledge graph or knowledge base from literature. And based on our extracted, say, chemical entities or relations, people can automatically generate some material synthesis plans and do some optimization. And those synthesis plans can be further fed into this robot system to conduct the real experiments for molecule synthesis. Last, I also want to explore new applications by extending text mining in other fields. For example, say nutritional science, material science, finance, or those cyber physical systems. I think any domain, if they have massive text data and they have this need for knowledge extraction, then there's a potential collaboration opportunity. Last, I want to thank all my collaborators for all my work during my PhD study, including different departments at the UIUC and also cross-university collaborations with other universities and institutions. Yeah, I think that's it for my talk, and thank you very much for your attention. I will also be happy to answer any questions.
So thank you very much. This was very interesting. I'm going to use my chair's privileges here and make the first comments and ask the first questions. So when we privately talked, I didn't mention this, but my group has worked on medical ontology since 1993, including a lot of work on the UMLS and on SNOMED-CT. And one chemical ontology is CHEBI, C-H-E-B-I, which you didn't mention. So you might want to look into this. These are chemical entities of biomedical interest. So so that's an interesting one. So a couple, I don't know if this is a question or comment, but when you talked about aminotransferase or telomerase, these are all enzymes. So what I was waiting for is that the next page that is going to come will have chemical followed by enzyme. But what is the reason that in a way you left alone the enzymes and didn't abstract those along the lines of the ontology?
So let me see. You mean in the chemistry ontology or?
No, in fairly near the beginning. Fairly near the beginning when you made the sentence patterns. Yeah, exactly. So if you look at this in the middle of the lines, it says chemical, right? And the aminotransferase equals protein. So I was wondering why you don't have the next line as chemical followed by enzyme, followed by protein. So it seems you selectively chose where you are going up in the ontology and where you're staying at the basic level. I was just wondering about that.
I see. Yes. That's actually a very great question. If we have a type enzyme, if we can recognize this aminotransferase as an enzyme, then we will definitely dig out this pattern, chemical enzyme, and we will further try to see like whether chemical enzyme refers to say some enzyme or some protein or some others. Yes. Here I just use it as an example. Say if we can only detect a part of it, then how we correct it. Yes.
I see. But bottom line is, I think you would have a number of collaborators at NJIT. Now that I saw your talk, I see this much more so than I saw before. Okay, other questions? Please, I guess, just start speaking.
Excuse me.
Yeah.
Can I go? Can I go ahead?
Who is this? Please identify yourself.
My name is Dr. Esther. I'm from the King Abdulaziz University from Saudi Arabia, Jeddah.
Okay.
Okay. I have actually written the question. That's first of all, I appreciate your talk on this particular about the chip banner and all this methodology you have discussed. As the doctor has rightly pointed out about the enzymes, that was also one of the some doubt about it. So my question, my work is on genomes. You know, I work in genomic data and single nucleotide polymorphisms, SNPs. So my question is that, can we work on the genomic data to explore the SNPs? And also the related question is that, how we eliminate the ambiguity of the huge data by using these methods to identify the new disease or novel genes in the genomes? I'm clear?
Yes, so I'm
If you
let
could
me
just
check.
for us computer scientists say what SNPs are.
Yeah.
I have just written the question also. Can you please?
Yeah. So for we are mostly computer scientists. So could you let us know what SNP stands for?
These SNPs are in the genome, we identify these single nucleotide polymorphisms, which are responsible to predict the disease. Because yeah.
Okay, thank you.
I see. I think it is possible. Although those my previous methods are mainly developed on text, I think there is a possibility to transfer those text mining techniques to genomic data analysis. Because they have some similarities. They are both sequence data, and also I guess for the genomic data, they also have some kind of grammars similarly to those text data here. And in terms of SNPs, I'm not quite sure like how you what you want to explore here. I guess if you want to identify those, probably it can be a similar task as how we identify entities in text strings, like how you identify SNPs in the genomic data. And how to eliminate ambiguity of huge data. I'm not sure what kind of ambiguity you are referring to here in the genomic data. In text, we do have many ambiguity that's basically because we need to have a deeper understanding of the local context. As we mentioned, for a single entity, like a phrase here, it can have multiple types, it can have multiple meanings, but under certain context, if you look at the sentence or paragraph surrounding, it usually have a very focused or certain meaning. That's how the text mining methods are trying to de-ambiguate those kind of things by looking at the context to find the most appropriate type of meaning for a certain phrase under the certain context. So I'm not sure if there are similar problems with genomic data. Probably we need to see the concrete problem here. And also identify certain diseases. In text, if you refer to identifying those names of new diseases, I think those anti-recognition methods is one way to do it. But in terms of genomic data, if you are looking at some association studies, say how this SNP or how this gene mutation is related to certain diseases, I guess probably some of those contrastive analysis we have done can be helpful here. Say if you have several comparable groups of diseases and you have say certain genomic data associated with each of those, probably we can do some comparative analysis to narrow down the candidates to find the most prominent ones, the prominent gene or mutations for each disease. I think probably this philosophy can be applied in a scenario.
Okay, thank you very much. Anybody else has any questions to ask?
Yeah. So I'm Haifan. I have a questions regarding to the gene NER, right? Basically, you apply a lot of techniques, ontology and like NER techniques, existing one and so on. And then like at the end of the day, you show that you achieve a superior performance, like 0.46 something compared with the state of the art only 0.2. So my question is, so what are the key components that make your algorithm so so good? And how to evaluate it. So which I don't understand what makes it so great.
I see. Yes. So I think for those for those baseline methods, for example, those distant NER methods, they assume they can work well in the directly KB matched results. So all our compared methods, we take a KB matching as the input training data or the initially labeled data, so that everyone deal with this directly KB matched data. In terms of how to deal with those data, our major improvements are in these two sections. First is during the KB matching process, we leverage this flexible matching so that we will be able to assign more candidate types to more those complex names in a text. This is the first step to improve the recall of candidate assignment. Second improvement is in this disambiguation, because for some distant NER, some previous methods, they do not do a very specific disambiguation. They just assign equal probability to all the possible candidates here. For example, this auto NER, when an entity is assigned to multiple candidates, it just assigns equal probability to them during the training process. And that's why they do not achieve a very good performance. However, for us, we specifically leverage the context information, also the ontology structure to do this automatic disambiguation, so that after this step, we will be able to generate much better or much cleaner labeled training data. Yeah, so I think these two steps, this automatic disambiguation based on ontology and also this flexible KB matching, are the two major steps to improve our performance.
Yeah, so in that case, the ontology basically plays a critical role.
Yes. In this work, the ontology is quite important.
So
we always knew that ontologies are important, right?
Yeah, but like the ontology is sometimes is have lots of error, and it's very difficult to generalize to all the domains.
Yes.
So if we don't have a good ontology, then the whole approach is not gonna work.
Yeah, that's right. Yeah. So for us currently, for this ontology building here, actually we also has many rounds of discussion in this part. We try to find the ontology from different sources, like Microsoft, they have the academic graph, they have this fine-grained the chemistry type, and also Wikipedia, also PubChem, many different sources. Currently this step, in order to make it reliable for our use, we do need human curation. Like our ontology is human curated, and also we cannot work on a very large one. Say here, although it's fine-grained is like less than 100 types, we cannot work on tens of thousands of types that human cannot easily curate. So yeah, for this work, this ontology, we assume is already constructed and is well functioning. In terms of other domains, if they do not have this kind of good or clean ontology, yeah, we do need a lot of efforts, say how we can automatically build and expand the ontology. Yeah, I think that could be another big research direction.
Yeah, and also it doesn't matter like the new ontology, the new domains. Within this domain, if you have a new disease or like basically a new like concept or something emerge, is so the ontology needed to be updated like very oftenly, right? Or otherwise, like how could the approach gonna catch up with the development of
Mhm.
you know, like real world.
Yeah,
Yeah,
yes.
which is actually a whole research area of syndromic surveillance.
Yeah, so that is one of the like questions I'm not sure, like, you know, like when we have a new problem to solve, then how reliable, you know, like the result is, and so on. It depends on too many components and how we evaluate each of them.
Mhm.
Like right now, I can see that you evaluate the whole system at once.
Mhm.
How could we evaluate each of them? So what is the impact of each of the component to like the superior performance? That is the unclear things. I still like.
I see.
Not clear to me.
Yeah, let me see if I have my ablation result here. So for my own study, probably I do not have the ablation table. I do evaluate the contribution of each component in my NER method, like how much. Sorry, I do not have the result. Yeah, but I do have an evaluation like how much the flexible KB contributed, how much the disambiguation contributed. Yeah, but actually ontology construction is not my work. So I do not evaluate it. I just take it as an input. Yeah.
Yeah, I also think we're going too deep into one single issue now. And it's 3:32, by the way. So maybe we just allow one single question from another audience member. Okay, no more questions. So I don't know. Do you have somebody else scheduled for 3:30 or 4 o'clock, or what's on your schedule now?
Yeah, I think at 3:30 I have a meeting with a dean, I think.
Okay, so we'll definitely have to stop then. So thank you very much for your presentation. I found it extremely interesting.
Yeah, thank you. Thank you, everyone. Yeah.
Thank you, everybody, for attending.